Hello, everybody. Can you hear me?
Yes. Hello.
Okay, just give me a second to share my screen. So, can you see my presentation now?
Yes.
Yeah, okay. So my name is Waddah Ali. I will start. I'm introducing EMG-based grasping forces estimation for robot skill transfer learning. I'm a PhD student at ITMA University. I'm working onto this research topic. First of all, I'm introducing you to the main approach to highlight the part that I worked on in this paper. So this approach is to teach a robotic manipulator a human skill from human biological signals and passive movements demonstrations during contact-rich tasks. This approach, in this approach, we have a policy. We have to propose a policy to build into to transfer both the recorded biological signals from muscle activities from human, alongside with the joint trajectories as input data to teach the robot to replicate these skills as a human does. So here in this policy, we built an ML model to predict the muscle grasping and manipulation forces from the recorded EMG signals, and the DMP and GMR, which are not included here in this proposed article yet. So keep looking on the ML model. We have the input, as I said, EMG signals from CMG electrodes during manipulation or grasping, where we have about 24 channels for those EMGs are distributed on the human arm by 3 bracelet patterns. And we have a sensor, an FT sensor to record the forces according to these signals to train the ML model that we are proposing. So talking about the ML model, actually I built a pipeline of compensating two models, concatenation of two models, MLP regressor, which is an artificial neural network one, and random forest regressor, in order to address the problem of nonlinearity between the predictors or features as EMGs and the measured forces and torques as a target. In this model, we've built the pipeline and used the ridge regressor in order to generalize as a regulator to the weights of these models in order to prevent overfitting and underfitting problems and sensitivity to the range of input. We used for our work metrics for evaluating the model prediction as the coefficient of determination, mean absolute error, and mean squared error, which are the famous metrics for evaluation of the regression models. Here we are illustrating the inputs and outputs. Here we have about 24 channels for EMG signals, which are recording human arm muscles, and 10 forces records for each finger. 2 forces for each finger. We are here addressing the problem of grasping as an application for our approach. So we have here 10 forces for 5 fingers of a human arm. First of all, we did the data processing step to take the EMG force profile pre-processing. The process is to filter those signals using multi-notch filters and Butterworth random bandpath filter, construct the filtered EMG force data frame, and clean those data from nans and infinite values and reduction of outliers. Then to rescale those values for the standard scaler in order to make it faster and simpler for the gradient descent algorithm in case of MLP model to be convergent and faster. The hyperparameter that we tuned in this approach is for the random forest regressor. We tuned the post-trap max depth, max features, and mean sample splits mean samples leaf, and a number of estimators using the randomized search and grid search algorithms for hyperparameter tuning. And for the case of artificial neural network, we tuned the batch size epochs, number of epochs, learning rate, and number of layers and nodes and to measure, and we had an early stopping callbacks in order to stop training whenever there is no enhancement of the training in 2-3 sequential epochs. We use the model to evaluate this training process. We use key-fault cross-validation. Here we see, after tuning those parameters, first we had some high value of prediction during training process, but in validation we have less accuracy. So we say that this is an overfitting problem that was addressed by adding dropouts for the MLP model and depending on the ridge regressor to evaluate to enhance the performance of the random forest. And after adding the dropouts, we got about 80% of accuracy for both the training and validation processes in both the random forest regressor and artificial, the MLP one. We compared our results with the state of arc RNN model, which is the recurrent neural network, is highly adapted for the time series data. And we found that our model with these modifications and tuning outperformed the performance of this model for this data. As you can see here, we have a mean squared error 0.27, while the RNN one is about 0.45. Here I'm illustrating the results with the plots that I've illustrated first for the forces. Here we see how our model can predict the results, the forces in comparison with the random RNN model. And here we can see some noisiness of the results because the model is predicting in each time 10 values for each force. So we have to consider the mean of these values to find the final production. And we see from here that our model fits the predictions in higher accuracy than the RNN model. This was what we've done, and thank you for listening and waiting for your questions.
Thank you very much for the presentation. Do you have any questions from people attending online? Please unmute yourself and ask if you have questions. Are there any questions from or I mean, maybe while you think I can ask a few. In your presentation, you were talking about grass force estimation. There have been other methods before this, the ones that you propose, right?
Yeah.
So can you give me like maybe a short outline in terms of accuracy and computational tools? How does it compare to the state of the art?
Actually, in this field of study, yeah. Okay. Yeah, actually, in this field of study, all of the research were done for classification of the hand gestures from EMG signals. Not all of research, not many researchers have addressed the problem of estimating the forces from the muscle signals. But in our case, and those tell us that estimated such thing were related to the control to the impedance control approach to have to modulate the stiffness patterns matrices for these controllers. But in our case, we are depending a new approach, depending on learning rather than controlling. In this case, we need to define, to address the problem of estimating the forces from the recorded muscles rather than just classification of hand gestures, as much as it is it's very important for us for contact-rich tasks where the coordination between the forces and the locations are needed, are highly connected to related to each other for assembly tasks, for example. So we see that we need to spread our work onto two trajectories. First one for the gestured and trajectory imitation, which we will do in the DMP's model, dynamic movement primitives, which is not of our concern in this article. And the first part was to estimate the forces and torques from recorded human EMG signals in order to provide with a methodology, a new methodology to train and to teach the robots how to do tasks without any traditional programming or controlling. So the research is novice, and not a lot of researches have been done before in such direction.
Thank you for such a lot of explanation. So, any questions from the audience or online? If not, let me thank you as a presenter. Thank you so much for your great presentation. Next one will be we'll ask to present authors of functional brain state after COVID-19, time and spatial domain patterns. The presenter.
Ali, can you please stop sharing?
Yeah. Okay. Thank you. Sorry.
Thank you.
Okay.
Marina Isaeva, Darya Vorontsova, Menshikov, Aleksandr Zubov, Kirill Orlov, Alexandra Bernadotte. Any of you online?
Yeah, I'm here. I'm Darya Vorontsova. Yeah. Alexandra Bernadotte also here.
Great, thank you so much. So you can present your work.
Yeah. Can you see my presentation now?
Yeah.
Yes,
okay.
it's, your picture is cropped. There's something wrong.
Okay, that's strange. I will demonstrate.
If you can share the whole screen or something.
And
yes.
Now it's better?
Yes, better.
Oh, it's cool. In our research, we were interested in frequency, temporal, and spatial domain patterns of electrical activity in people who have undergone COVID-19. A little history. While developing an AG-based BCI, we came across a significant inhomogeneity of the AG data. Given the COVID-19 situation with more than 500 million confirmed cases around the world and more than 6 million deaths, we hypothesized what this heterogeneity may be related to the neurological consequences of COVID-19. Previously, we showed that despite the noisy signal of the AG data reveals patterns characteristic of the internal pronunciation of word monument commands. That is, despite the prejudice against the noises of the AG signals, these signals provide meaningful data about very subtle processes of mental functioning. And also in our paper, we presented a binary classifier based on a convolution and recurrent neural network, showed accuracy equal to 60 on average with a maximum value of 78.9 when classifying AG data from people who have undergone SARS-CoV-2 and people who didn't meet the SARS criteria. On this slide, you can see the information about our dataset. And a little about experiment. Each experiment lasted from 5 to 14 sessions, depending on the subject's condition. And also, each session consisted of showing 10 words from the training dictionary in random order with repetition allowed. During each session, every subject were asked to pronounce the word shown on the screen aloud, the verbalized speech or silently imaginary speech without removing AG. Also at the screen, you can see information about data what we choose for our research. It is 22 individuals who were diagnosed with COVID-19 and 21 who were not. And our data pre-processing on the right side of screen, you can see the scheme of pre-processing. And first, we cut the AG data into 2D vectors, 1024 long, with about 4 seconds, considering the sampling rate is equal to 250 Hertz and 32 wide, which is the number of AG channels. Second, we duplicate H channels. And at this picture, you can see these channels highlighted as in blue and red. After this, using the downsampling algorithm, the sample rate was downsampled from 250 Hertz to 125 Hertz. And the data were split into 2 separate samples with dimensional 4, with dimensional 42 and 1024. When we picked the result samples into 2D vectors and get 512 fast Fourier transforms components and cut off the first half into 2D vectors 80 to 256 dimension. And in parallel, the sampling rate was downsampled from 125 Hertz to 62.5 Hertz. And the resulting samples were packed into a 2D vector 160 to 256. Also, in parallel, we using the eye noise filtering presented above, and we obtained 6 components of eye noise from 6 groups of channels. Finally, taking into account the separation of electrode into the left and right hemispheres, we combined vector into a 2D vector with the dimension 256 to 256. This is our resulting vector, and here eye noise of the left hemisphere when downsampled tensor from the left hemisphere, median from FC5 and C5 channels, and also downsampled tensor from the left and right hemisphere respectively, and where medians from FC6 and C6 channels, downsampled tensor from the right hemisphere, and eye noise of the right hemisphere. So about classification tasks, we use 2 models. The first was based on convolution neural network ResNet-19 and 2 layers of gated recurrent unit. And the second model was also convolution neural network. It is DenseNet 121. And both models were selected due to their performance in our previous research. The train and validation set were constructed in a classical way, while the test part of the dataset was formed using an out-of-sample approach. Using these neural networks, we obtained the following results. And binary ResNet 19 plus 2 gated recurrent unit classification accuracy reached 66% on average, and DenseNet 63% on average. We see what we presented neural networks classifiers can separate AG data after COVID-19 from data which did not meet the COVID criteria. And for the 2D vector, 256 to 256, we applied a nullifying kernel of size 32 to 32 with height equal to 12 and padding equal to 0. And using pattern detection by this way, we use it on our neural networks. And result you can see at the screen. And the data obtained demonstrates the attention of the neural network to certain patterns from the spatial frequency and temporal domains. We see that there is a difference in perception attention when assigning AG data to one of the class COVID-19 and non-COVID-19. This difference in perception suggests that a combination of patterns is important for classification. We found a predominance of alpha rhythm patterns in the left hemisphere in healthy people compared with people who have had COVID-19. Also, we see a significant decrease in the contribution of alpha rhythm in the AG signal in both hemispheres in people who have undergone COVID-19. And moreover, we observe a significant decrease in the contribution of the left hemisphere in the area of speech center and in people who have had COVID-19 when performing speech tasks. Normally, loss of alpha rhythm indicates overstrain of the brain while concentrating on task. And also, the data show that the signal in healthy people is more spatially localized and synchronized between the hemispheres when performing tasks when in people who have undergone COVID-19. There is no frequency synchronization of the hemispheres, and there is a decrease in low frequencies in the activity of both hemispheres in people who have had COVID-19. And also we observe a significant increase in contribution of high frequency to the AG signals in the right hemisphere in people who have had COVID-19. So thank you for your attention. Yeah.
Was a great presentation. Anyone in the room have a question to the presenter? Yeah, of course. But I really would like to ask. When you start your research, you had some ideas why COVID should contribute to differences between COVID and COVID-free and COVID people who were young with COVID. So what physiological background of the research? What are implications? I could not find in your presentation background why did you decide to test this data, or what are implications? Very nice, but I would like to understand.
Yeah, okay. Alex Bernadotte will answer on this question because she here is better.
Hello, colleagues. If you don't mind, I would suggest myself to answer this question. So we actually started from the physiological part of the study, and it's not presented here in this presentation because it is actually quite detailed described in the paper. First of all, anyway, I'm gonna do it right now. So first of all, those people who undergone COVID-19, they have patterns of neuroinflammation, and we were trying to find them using our brain-computer interface based on EEG data. As you saw, we actually found quite impressive results that there are differences in people who were suffering from COVID and those who didn't meet any criteria of COVID-19. First of all, there were noisy brain. We can find it means that there are kind of really high frequencies were much more pronounced in people who were suffering after COVID-19. And it's quite common for aging brain. It's quite common for neuroinflammation itself. It's quite common for Alzheimer's disease and other. So after this research, we would say that brain after COVID can demonstrate itself at the aging brain, at the early aging brain. We see patterns in low frequencies, more pronounced frequencies in alpha domain, which means that it is kind of sleepy brain, and we see patterns in high frequencies, which means it is kind of aging brain. So does it make sense?
Thank you for such a good answer. Anyone in the room or online, maybe if someone online wants to ask a question, please unmute to talk. While people think, I wanted to also ask, maybe again slightly naive, previous speaker. I think part of the premise is that you can divide people based on this one metric. For example, they had COVID before, you even accounted for vaccination. Like your data set has people who had COVID versus people who did not have a COVID and neither had antibodies or were vaccinated. What I want to know if such a division, taking into account how much of the population had COVID in the past 2 years, can introduce its own bias, as in maybe it is a specific type of people who did not have COVID after 2 years of the pandemic, right? So what I'm interested in is could the bias of selection of this other group, control group, have influenced the results, in your opinion?
Thank you for your question. It's really kind of really smart question because we were wondering ourselves. We were asking ourselves the same questions, and we are actually preparing another paper, much more extended paper. And in our future paper, we will show that there are differences between people who were undergone COVID and were vaccinated before, and those people who haven't been vaccinated before they undergone the COVID. But actually the results are quite slight because of our set, the limitation of our set. And anyway, we do have results showing that vaccination is kind of really necessary, what all of us have to do to protect ourselves from aging brain and from dementia and from neuroinflammation, early dementia, and so on. We do see those patterns in people who were suffering COVID without being vaccinated earlier. So thank you for your questions. The data are coming. They're going to be published very soon.
Yeah, no, thank you. And I guess, not to elaborate too much on my question, but what I was worried about is that the data set which you compare would be a data set mostly of, let's say, people who live secluded lives, or people who suffered from, previous illness that made them unable to participate in social life, or something else that kind of led to them being unaffected by, the wave of pandemic and thus they were able to both avoid vaccination and be infected. Which you can imagine this could influence the brain patterns. While like having a clean data set of exactly the same people, but some affected, some unaffected, that sounds to me a little bit more challenging. I don't know how you.
Right. You're actually looking in the future because we have another paper prepared. We are working on the brain difference we can detect on brain-computer interface based on EEG data between people from different occupation, education, age, and so on. We do see difference. Here we did not show this kind of data because we want to focus ourselves on COVID data and be a bit more strict on the message that we have to vaccinate ourselves, otherwise we are in a risk of neurodegeneration. And you're absolutely right. There are a lot of slight differences in people from different social experience. You're actually really right. And we are preparing another paper. It's coming soon as well. So you're going to be posted, if you don't mind.
The message was something that we probably all need to hear. If there are no more questions from the room, let me thank you again. It was a great presentation. It was very interesting. And with that, I would ask. I would ask the next presenters. It is a paper optimization of the brain command dictionary in silent speech recognition task based on statistical proximity criterion. And the presenter will be Alexandra Bernadotte.
Yes. Hello. Can you see me? Can you see me?
Yeah, but you can see the slides.
Okay, great. Do you want me to share it? Is it fine?
Yeah, it looks fine.
Yeah, this is much better.
Okay, great. So in our research, we will focus on the task of classification of silent speech recognition with the goal of developing EEG brain-computer interface. And we were developing in an EEG brain-computer interface, which will be capable to assist people with mental and physical disabilities and expanding human capabilities in everyday life. In our previous work, we showed that people belonging to several common social categories share similar brain signals patterns, allowing us to divide the dataset in the corresponding group and train neural network separately for each of those groups. Our previous research has shown that silent pronouncing some words result in almost identical distributions of brain signals data. Such phenomenon has a suppressive impact on the quality of neural network behavior. In our present research, we wanted to approach this semantic and articulatory proximity of different words in a very particular way, in a very practical way. We wanted to build such a dictionary so the word with different meaning could be easily separated by our neural network. For our practical vocabulary, it's not so important that synonyms will be poorly distinguished by brain-computer interface. On the contrary, it is much more important that words with different meanings can be distinguished with the high quality. Earlier, we showed that there is a silent speech classification problem can be overcome by selecting a correct dictionary of well-recognized and accurately classified words. So there is a scheme here. Previously, our group presented a graph dictionary selection algorithm, and I'm showing it here, applied to the algorithm to our data. The selection of the dictionary itself is rather labor task, and we had an idea to develop a certain criteria that would allow us to predict the behavior of the neural network. At the same time, it would be quite convenient in terms of time and resources. Thus, we were looking for a criteria in the field of statistical methods, which would be less expensive in terms of calculating resources. The new study presented in this research were based on the analysis of classification behavior of neural networks trained on a set of EEG data recorded on our on-device brain-computer interface during several sessions, and those records were corresponding to silent speech of words up, Vera, and down, minor. Those words are semantically divided into two classes, up and Vera, which means up, and down and minor, they both mean down. To avoid time and GPU resources consuming, dictionary selection was kind of interesting for us to consider. And we actually considered to find a predictive criteria by which we could predict the results of the binary classification. And binary classifications were used actually for algorithm I described before. So we were trying to find the existence of criteria by which we could predict the results of binary classification of a neural network. Thinking about the predictivity of Criterion for neural network classification accuracy, we formulated the following hypothesis. Conforming these hypotheses and gaining the new knowledge about the patterns of brain activity aim at improving our classification results, not only by training architecture, but also by intelligently turning the dictionary with particular attention on the dictionary. And I would say actually that in particular, we show that the sum of all p-values computed pairwise for every two classes in the trained dataset can be used to make estimation of the accuracy rate of the neural networks we were using. So there is a slide of our dataset. All our subjects has reached adulthood. They were healthy, signed voluntary consent to the study. The subject could interrupt the study at any time without explanation. The subjects provided the data which include gender, age, education, and occupation. The exclusion criteria for the study were history of head trauma, alcohol, and other intoxication and epilepsy. So the dataset we used for our study consisted of 33 channel device, EEG channel device, recording completed at 250 hertz during several sessions, and that's it. There is our scheme. The scheme was classical scheme for placing electrodes, traditional 1, 10, 20. So data processing. First of all, what we are doing, we were doing a noise filtering procedure consisting of morphological selection of eye-sensitive channels, independent component analysis, and further detection of the eye noise component using fast Fourier transform, Savitsky-Gallet filtering, and inverse fast Fourier transform. Second, we were filtering out the tensors with a high noise level by applying two different filters by the sum of moduli of the signal amplitude. So we were removing actually outliers from our data. Then we were downsampling the sample rate by using special index mask on the original EEG data. We were separating electrodes in two hemispheres, left and right hemispheres. We were reorganizing the elements of data in order to form two-dimensional matrix we can use in convolutional neural network input. So before using the criteria, it is strongly recommended to use principal component analysis. After principal component analysis, we can look at distribution of mental words, e.g. mental words, at the distribution of 2D space. We actually use 3D space. The Kolmogorov-Smirnov test, independent of nature of the distribution, was applied to the set of distributions in 3D space by computing the set of pairwise p-values on train, validation, and test sets. Each component, or we can say dimension, has its own p-value. The minimum p-value was taken from this set. The existence pairs of synonyms were organized in ascending order of the p-values. So we actually rank our words by their p-values on I forgot the word, classification, 2K classification accuracy. So the predictive criterion was based on statistical of dimensionally reduced data, the set of all possible p-values of Kolmogorov-Smirnov test on PCA dimension reduced distribution from validation and train sets. The p-value and the network binary classification accuracy are inversely correlated. So the neural networks we were choosing. So neural network classification models which were tested for multi-class classification for various set of words included visual transformer and convolutional network ResNext 18. Actually, there were a lot of neural networks before the study we tested, but we decided to choose those two because they provided best accuracy for our study. So the main feature that makes ResNext 18 model differ from convolutional residual networks is the introduction of cardinality hyperparameter, which separates channels of the input tensor into several groups, which each one being operated its own convolution kernel. So we can use each convolution kernel for the separate channel. So visual transform. The architecture of vision transformer is aimed to dealing with the square images, like all of our networks we were choosing were dealing actually with the square images. We are preparing our data in this way. So visual transformer was able to crop into numbers for square patches of similar sizes. So those patches serve the input to the trainable part of the network. So results. We applied Kolmogorov-Smirnov test for every pair of classes in initial dictionary. So initial dictionary consisted of 4 words, up, down, vira, minor. So all those words were presented in 3D space domain. After the set of p-values is computed for each of 3 components, I mean 3 dimensions of the data, the minimum value is chosen to indicate the degree of statistical separability between 2 classes. So we were choosing the minimum value or p-value, minimum p-value, which means that those words are separated better than others. The results of Kolmogorov-Smirnov test computed separately for train, validation, and test sets, and they're presented in the table. We were testing the work of the classifiers on various deep neural network architectures, including convolutional networks and transformers. And we actually, as I said before, among convolutional architectures, we tried ResNet 18, ResNext 18, ResNext 50, 101, 152. We created a 6 copy for the study for this one. We created 6 copies for of the networks with various weight initialization and launch training procedure for each of them separately. The highest score of results were obtained by implementing ResNext 18 neural network And that's why we decided to apply it for our study. The result of ResNet's 18 and transformer application for the data set are shown in this table. Consider a pair of words, I and J, and from the dictionary of 4, and let's denote P with TR. The P obtained from Kolmogorov-Smirnov test for words, for those 2 words on the training set, and P-val on the validation set. So we've got this kind of data considered as the criteria for neural network prediction accuracy. And another slide showing the same similar criteria, predictive criteria for vision transformer. And here we can combine in the general criteria. We can combine both to generate general criterion. The general criterion, which is presented here, is true for both considered classifiers and allows to predict the results of both networks with the estimated classification accuracy. It can be noticed that Kolmogorov-Smirnov test applied towards up and down. Here, up and down. And Vera and minor results in significantly higher p-value, and we see the same here. And we can show that those words, those couples are statistically approximate. And I'm going to conclusion. In this work, we have shown the fundamental possibility of working with the low-dimensional data and reducing resources consumption for selecting the optimal dictionary for brain-computer interface based on EEG data and for silent speech recognition. We formulated and confirmed the hypothesis about the existence of predictive criterion based on distribution statistics of data with reduced dimension and predicting the accuracy of classification by a neural network on the same data of a higher dimension. Third, we also showed that higher levels of p-value between the classes lead to degradation of classification behavior. In particular, by applying the data processing approach proposed in this research, we proposed that a data set consisting of 2 statistically remote words yields significantly higher accuracy metrics in the task of binary classification than a data set with 2 statistically close words. And we can see that there is a pattern between statistical proximity between words which were widespread, and those words were statistically remote, and they actually are unfrequently used. And the application of Kolmogorov-Smirnov test showed that electrical patterns produced by silent speech of words up and down share the same statistical patterns. And finally, we applied our approach to our data, and we showed that we can increase the accuracy score using the same architecture of our neural network from 50% to 92% on the same data, on out-of-sample test data. And if we use a special dictionary, the special dictionary we formed using our predictive criteria. So I would say that's all what I would like to share with you. Thank you for your attention.
Thank you very much. Anyone in the audience have questions? Present. If anyone who is joining online wants to ask a question, please go ahead and unmute and talk. again, while thinking, I'd like to ask, do you think silent speech can be used to recognize without prior, how should I put it, like calibration of the device to a particular person? Or do you think if you need a person to use silent speech to produce commands, you first have to calibrate the device for that person?
I used to get really smart questions from you. So we're actually preparing another paper as well, where we are considering, and actually another one was published. We were hypothesizing that there were kind of paradigm. First of all, can we calibrate or train our brain-computer interface based or on EEG data using convolutional neural networks? Should we calibrate it on one person, or should we extend our data set? And we were actually trying to answer this question, and we found the answer. So it's better, surely, it's better to train on one person if you want to use this brain-computer interface on the same person. So you have to choose. You want to make it universal, or you adopt your brain-computer interface to the person, especially using these pre-trained or, as you said, calibration techniques. So we decided to make a brain-computer interface which can be adopted, using kind of invariant patterns of the population. And we found that there are differences between people having experiencing different occupation and education and so on. It was shown before that there were different patterns in thinking for people from different language groups. So I've been doing myself in my master program research, which was showing that Canadian people who were speaking French, they were, and it was not their first language, but very close to first. They were learning French in very early age, like 2 or 3, but their parents were English speaking. And we can see that there is a slight difference between real French people, native French people, and people who were studying French later. And we can see the difference in thinking for people having English as a native, and people who having Russian as a native language, and so on. So we actually our brain is quite well. It's quite common sense that our brain is undergone different experience, and all of them, it's like fingerprints of our brain on our brain. So we have to consider the difference in our population, but we would prefer to make brain-computer interface which can be used for the majority of the population. So did I answer your question?
Yeah, just one clarification, if I may. So if it is in some circumstances possible to find a word that a person can use to give commands to a device that was not tuned specifically for them, this somehow implies that using this device, you can find some sort of universal like signifier in terms of like your EEG signals that is mapped directly to this word, which seems to be like a quite significant statement in terms of linguistics, theory of language, etc. As in, you can map a word to a physical state. Is that true?
again, really smart question. So we were wondering, we were asking ourselves the same question as well. So there are some papers showing that we can find some patterns, EEG patterns in the brain for particular words. Like, do you remember the paper like babushka neuron, grandmother's neuron? Do you remember this paper?
No, I'm not even like from neuroscience.
Oh, okay. Okay, got it. So we can find even one neuron responsible for some kind of word or thought and so on. But I would not say we can find invariant pattern, and we can directly say that this person, without knowing anything about this person in particular moment thinks the particular word. We can say that possibly this person is thinking about something emotional for this person, because we actually can find we actually can distinguish emotional charge words from words from natural words. We can say it. We can distinguish words we commonly use words from those used infrequently, and we can actually I showed this data in our paper, and we can say that the person who are studying math can be identified by EEG data. But we cannot say that knowing anything about this person, know anything about the language group of this person, didn't get any EEG data from this person. We cannot say that the person is thinking the particular thing. So we cannot read brain. We cannot read thoughts. We can read commands if we train on those people, group of people, or particular person. Does it make sense?
Yeah, it does. Thank you. It was very explicit. Thank you very much. I mean, we somehow
Thank you.
Those two presentations into like a best for people who are not from neuroscience. Now we know much more than we did before the session started. Thank you so much.
Thank you. It was really nice talking to you.
No, thank you. If there are no more questions from the audience, then I would like to invite the next presentation, the study of biological aging mechanism of the human neuromuscular system based on statistical analysis of physiological signals. It is Valery Yunusov, Sergey Demin, Alexandr, Elenev.
So my name is Valentin Yunusov. I present our work, the study of biological aging mechanisms of the human neuromuscular system based on statistical analysis of physiological signals. The object of our study is a brain or neuromuscular system. It is a complex system. Complex systems play a special place in the variety of objects of the surrounding world. The signals of complex systems are often presented as time series of time series are the dynamic variables and spatial maps of the structural characteristics of complex systems. Complex systems carry essential information about their evolution, which can be extracted using the methods of statistical analysis. Recently, the demand in this area has increased significantly due to the development of machine learning methods. In this paper, we study the physical mechanisms of human biological aging. Most often, this phenomenon is described as an inevitable biological process of gradual degradation of individual organs, tissues, and the organism as a whole. We use the analysis of physiological signals based on the human neuromuscular system. From the point of view of the physics of complex systems, the physiological complexity underlying the physical mechanisms of biological aging is of interest. There are various quality and quantity criteria of describing the human aging process, which are presented on the slide. Scientists are constantly making attempts to find optimal mathematical models and methods for a quantitative description of the aging mechanisms. There are various approaches and numerical methods for analyzing collective phenomena, synchronization effects for description of temporal dynamics and evolution of complex systems. They are presented on the slide with the result. The memory function formalism, which we use in our research, is a discrete generalization of transit memory formalism used to study the stochastic dynamics of complex systems. The proposed approach is based on the representation of the studied process in form of multi-dimensional state vector. To describe the dynamic properties of the complex system under study, it's convenient to use the normalized time correlation function, which is given as presented at the bottom of the slide. Within the framework of the approach for the studied time series, a chain of finite difference linked kinetic equations of the transit memory type is constructed for the time correlation function and statistical memory functions, which are presented at the head of the slide, for interrelated variables. In particular, to describe the statistical memory effects, the parameter epsilon1, or Markov's parameter, which is presented at the bottom of the slide, is introduced, which allows comparing the relaxation times of the time correlation function and the lifetimes of the statistical memory. In the case of epsilon1 being much larger than 1, the process under study is characterized by short-term or weak statistical memory. With a parameter value comparable to 1, the process under study is characterized by a long-term or strong statistical memory. Data under study as a result of the synergetic activity of the human muscular and nervous system, recording of dynamometric signals. A round dynamometric sensor was fixed on the table. The wrist, middle fingers, ring fingers, and little fingers were also fixed. The analog signal was amplified and converted to digital format. At the preparatory stage, subjects from 3 age groups press the dynamometer sensor with maximum force with the side of the index finger. Table on the slide provides a description of the perceptions in this study. After that, the subjects press the sensor with a force of 5, 10, 20, and 40 of the maximum pressing force. Compliance with the required pressure value on the sensor was carried out by visual control. The participants in the experiment saw 2 lines on the monitor screen, the calculated and experimental values of the pressing force. The noted conditions for the recording dynamometric signals for subjects of different age groups allow concluding about age-related changes, not only on the human neuromuscular system, but also in visual motor coordination. On this slide, spread of parameter epsilon1 values calculated for the dynamometric signals for subjects from different age groups are presented. Calculation was performed for each level of pressing force in 2 attempts. Mean values of Markov's parameter are presented at the head of the plot. Comparison of the average values of the parameter indicates a twofold weakening of the memory effects for the signals of third group in comparison with the group of young volunteers. The weakening of the memory effects of visual motor coordination with age leads to an increase in stochastic components in the regulation of motor units by the human neuromuscular system. On this slide, figure shows the spread of values of relaxation times calculated for dynamometric signals for volunteers of 3 age groups. 2 attempts were recorded for each group. Calculation of relaxation times was conducted by estimating the area under the temporal correlation function determined for each dynamometric signal, as presented by formula at the head of the slide. Mean values of relaxation time parameters are presented at the head of the plot. Comparison of the average values of relaxation times for different age groups indicates a significant wavening of these times for subjects in second and third group, or the group of older subjects. In addition, in the case of young volunteers, increased pressure leads to a leveling of relaxation time, which, while in the case of representatives of second and third group, an ambiguous picture is observed. In our study, we developed various criteria of biological aging representation, and the obtained quantity criteria of biological aging may be helpful in the study of human coordination to solve the problem of movement of robotic devices after additional studies by different statistical methods, including machine learning methods. Attention. I'm now ready to answer your questions.
Thank you. So does anyone have questions? Maybe
It's actually this.
so anyone online have any questions? So maybe just a quick. Can you tell us where do you see the immediate application of the study you presented? Where do you think the particular not just the concept overall, but the particular content that you presented today can find its application?
I think the neuromuscular approach we used can be used to can be applied to the sensors of robotics means of the coordination and the, to accurately measure the force with which these robotics are doing things.
All right, thank you. Anyone in the audience have questions? All right, let me thank the presenter. Thank you so much, Valentin. And thank you. And now we have the last presentation for this session, formal asymptotics of parametric subresonance, presented by Polina Astafyeva and Oleg Kiselev.
Hello, everyone. Do you see my presentation?
Yes, we see it.
And my theme is formal asymptotic of parametric subresonance. And this linear equation of the form 1 are important models in mechanics. Any processes associated with oscillations are determined by second-order equations according to Newton's law. This equation has a general character. We will be interested in equations with time-dependent coefficients. And for example, if there is a spring, then Hooke's law works and the coefficient is constant. And if instead of a spring there is a nonlinear element, for example, a pendulum with a strong deviation, sinuses appear and the equation becomes nonlinear. And we are considering a linear equation with variable coefficients. They can occur when an external influence on the system. For example, if there is an atom with an electron in the outer orbit, then it can be affected by radiation, for example, light. Atom perceives it and there are vibration of the electron and it can go from an unexcited state to an excited one. Another example, the Hill equation describes the moon motions around the Earth, and the external effect is the effect of the sun, and as a result it turns out the equation with variable coefficients appear. In Mathieu periodic equations, there are zones in which solutions grow exponentially, and there are zones where solutions is limited. Equations with periodic coefficients and properties of solutions of equations with periodic coefficients were considered by such classic of science as Floquet, and it allowed us to understand the distribution of stable orbits of the electrode on the hydrogen atom. And if we consider a more complex system, for example, the movement of particles in Saturn's rings, Saturn's satellites act on the particles. There are divisions in the rings, there are regions with a small numbers of particles between them. This is explained by the fact that Saturn's satellites brought particles out of this zone due to resonance. Despite the fact that this equation has been studied for 2 centuries, a new one has been found. The coefficient is not periodic since there are no periodic one exactly. Therefore, we consider an almost periodic function, and it shows a special character. And the graph for an almost periodic function. And this is a typical picture for a non-resonant case. And for numerical solution, we used Runge-Kut method of 4th order. And the picture shows bounded oscillations for the equation. And this figure shows the subresonant growth at the initial interval. And let us construct an asymptotic solution in the following form. And the task is to find the dependencies of A and B with U being bounded. And we denote. And we got a system for W and V. For kappa equals to 0, the system splits into two separate equations. The solutions have the form W and V. The solution grows exponentially. For kappa is not equals 0, divide the left and right parts by kappa and after rewrite. And in this case, we get another system. And the system leads to a second-order differential equation. And here lambda is a large parameter, so asymptotic solution can be obtained by the WKB method. And so turning point to change the growing character of the solution is located in a neighborhood of the point theta. And let us compare the position of the turning point obtained here by asymptotical way and the result which were shown in the figure. From the numerical example, we have the following data. Here the growth cessation zone is shown in the figure. The area of the end of the growth is very far away, and if we were just doing numerical analysis, we would never have reached it. It is a result of analytical calculations, and numerical analysis confirmed this result. And the difference of these equations, Mathieu and equation with almost periodic function, is not only in the function before U, but the tau is a different variable. Matthew equation has exponentially increasing solutions, but not in the equation with an almost periodic function. And we can see at what times restrictions appear. To conclude, we obtained the system of equations for parametric subresonant growth of the amplitude of oscillations. And the growth depends on the slow variable tau. And we found also the time of the turning point from the growing of the amplitude to the bounded oscillations in the slow variable tau. And the comparison between the asymptotic approximation for the turning time and numerical one is found. And thank you for attention.
Thank you. Thank you for your presentation. Do we have questions to the presenter? Anyone in the audience or anyone who is joining us via call?
There's a question.
Thank you very much for the talk. Unfortunately, I'm not a mathematician, so my question will be very, very general. So as I understand, you studied the very specific case when the equation has the form where one of the terms is near harmonic, near oscillating. And can you give me an idea where in real world I can meet such kind of equation? And maybe you said it in the very beginning, I just lost the thread of your stuff. So where I can meet the case where this equation can appear?
I don't know exactly what can it appears, but I guess it appears in celestial mechanics, and maybe it can apply it in ultrasound control. And since the frequency are not poorly resonant.
Okay, thank you. So just to get to the main of your application. Thank you very much. Any other questions?
Anyone else wants to ask a question to the presenter? Well, by the way, if I may, you showed that you computed the solution to this ODE using Runge-Kutta first order method. The graphs that you showed, you generated them from a numerical solution, if I understand correctly. Is there any way to verify how close this numeric solution to a true solution, like a solution that turns a differential equation into a тождество, as we say in Russian? Is there a way to verify how much error accumulated in the numerical solution?
And I could use the only Runge-Kutta method. And I didn't catch your question.
Huh?
I think there's a. Yeah. No, it's okay. Sorry.
There are no more questions. I wanted to thank you. Thank you so much for your presentation. And I wanted to thank everyone else who presented today. It was a very interesting conversations and discussions. I would ask everyone to join us for the next session that will be starting soon after a short coffee break. It will be very interesting, I promise. There will be walking robots, flying robots, etc. Not only robots, too. There will be other things. So please come join us after the break. Thank you.